When working with Arduino, it is necessary to learn a few basic concepts in electricity and electronics, since Arduino in itself is an electrical device. So let's start off with Ohm's law. In chemistry or physics, an atom is the smallest constituent of all matter. And then the atom is consist of smaller particles, the proton, the electron, and the neutron. The proton has a positive charge, the electron has a negative charge, and the neutron has no charge or neutral. The charge is measured in unit coulomb. Now imagine that we have many atoms and then we start to extract their electrons, we remove their electrons, and then we start pushing those electrons such that they move or they cause a motion. Now, these moving electrons is what we call electricity or electron flow. Electricity is measured in unit ampere. Now, what caused this motion? Of course, there should be something that caused the electrons to move. It's like when you push a chair, it's falling because you push it, or a leaf from a tree is falling because of gravity. This energy that caused electrons to flow is what we call voltage. Voltage thus is the reason why electrons are moving. Voltage is measured in unit volts. Voltage can come from many different sources. Examples of voltage sources are batteries, solar panels, the AC wall outlet, or the 220 volts outlet. Of course, in any aspect of life, there's always something that opposes. In electricity, this is what we call the resistance. Resistance is the opposition to the flow of current. It is measured in unit ohms. Now, these three parameters, the voltage, current, and resistance, make up the Ohm's law. The Ohm's law states that voltage is equivalent to current multiplied to resistance. We can also say that current is proportional to voltage but inversely proportional to resistance. This relationship of voltage, current, and resistance can also mean that an increase in resistance will cause a decrease in current, or a decrease in resistance will cause an increase in current. Therefore, current and resistance are inversely proportional. So the Ohm's law is similar to this analogy. I have here two water tanks. Both of them have hose or pipes going down. One of the water tank has thicker hose and then the other has thinner hose. In this setup, the water represents electricity since it is the one that is flowing. The voltage or the energy that caused the electricity or the water to flow is gravity because of its position. And finally, resistance is the width or the size of the hose. The bigger the hose, more water will flow since the resistance is less. The smaller the hose, lesser water will flow since the resistance is high. The concept of Ohm's law is very basic, but if you understand it, it's very useful in your projects dealing with electronics as well as with Arduino. Some practical troubleshooting examples is like this. What does it mean when we say that it's short-circuited or nag-short circuit? It means that it's a literal short, meaning you've connected two wires directly. If you connect two wires directly, then the resistance is approaching zero. So, how much current do we have if we have a resistance of zero? We have infinite current, or we have a very big amount of current. That's why when we have a short circuit, big amounts of current flow through the wire, causing it to heat up, and then sometimes will cause it to make fire. On the other hand, if we have a very big resistance, then there is very small current that will flow. For example, if I have two wires over here, and then I place a rubber or a piece of cloth in between, then current will not flow because of the very high resistance introduced by the rubber or the cloth. So this type of materials that has very big resistance and does not allow current to flow is called insulator. Materials that have low resistance and cause electricity to flow much more easily are what we call conductors. What is the difference between DC and AC voltages? DC or direct current voltage has two terminals with a polarity, meaning one terminal is positive and the other is negative. The positive terminal is usually called VCC or VDD, or the voltage level itself, like 5 volts, 12 volts, or 24 volts, and so on, while the negative terminal is the common reference or the ground, GND. Direct current voltages have their currents flow in one direction only. Examples of DC voltages are those coming from car battery, AA battery, solar panels, solar cells. A DC voltage can be a positive DC voltage. It can also be a negative DC voltage or a pulsating DC voltage. AC or alternating current voltages also have two terminals, but they have no polarity, meaning you can connect them in any way without any orientation. Like you can connect it this way or that way. It's like in our 220 volts plug at home, we don't check the orientation, we just plug it directly. The flow of current in an AC voltage is actually alternating current flow in both directions, meaning it can flow in one direction and then afterwards it go back to the other direction. It has a certain frequency, how fast it changes its direction. We quantify it in terms of hertz. So basically, we have our household AC voltage at 220 volts and 60 hertz in the Philippines. Another example of an AC voltage source are generators. Generators can come from water turbines, geothermal plants, or hydroelectric plants, or from diesel or coal plants. An AC voltage can be sinusoidal like this. You can see that there is a positive alternation, and then it goes to zero, and then there's a negative alternation, and then go back again. You can also have a square wave or rectangular wave AC voltage like this, as long as one is positive and then the other end is negative. You can also have a triangular wave AC voltage. Now, let's define a very basic electrical circuit so that we can describe every electronic circuit. We have a source, electronic components or circuits, and load. The source can be a battery, a power supply, or AC line. It is the one generating energy that causes electron flow. In this case, we have DC. We have a positive and then the negative. The electronic components control or process current flow in order to produce an outcome. And then the load consumes the power or energy. It can be a light, motor, or antenna, or any other circuit. In dealing with electronics, it is very helpful to learn about a few basic electronic components. We have here a resistor. We all know that a resistor opposes the flow of current. It is also used to control the amount of current flowing through a load. This one is a discrete resistor component wherein you can see that there are color-coded bands. This one is a chip resistor which is surface mounted on a printed circuit board or PCB. This is the electrical symbol of a resistor. In a basic discrete resistor, we can have either a 4-band code or a 5-band code. The color bands represents the value of the resistor. For example, for a 5-band resistor, the first band represents the first digit of the value, the second band is the second digit, the third band is the third digit, the fourth band is the multiplier, and then the fifth band is the tolerance. Each color is represented by a number. For example, black is 0, brown 1, red 2, 3 orange, 4 yellow, 5 green, 6 blue, 7 violet, 8 gray, 9 white. Note that for the multiplier, we just multiply this number to the first 3 digits, the tolerance is just a manufacturing tolerance, usually 1% to 10%. As an example, we have orange in the first band, which is 3, green in the second band, which is 5, black in the third band, which is 0, red in the fourth band, which is a multiplier of 100, and brown in the fifth band, which is 1% tolerance. With this, we have 350 times the multiplier 100, then we have 35,000 ohms or 35 kilo ohms and 1% tolerance. Next electronic component is the diode. The diode limits the direction of current in one direction only. You notice that we have a band in one of the sides of the diode. This band usually represents the negative side or the cathode. The other end is the positive side or the anode. The electrical symbol for the diode is like this. The diode has a voltage drop of around 0.3 volts to 1 volt, usually at 0.7 volts. That's why the diode is also used to reduce the voltage by using its voltage drop. I have here two circuits. The one on the left has its battery with the terminal, the positive is on top and the negative at the bottom. The one on the right has its terminals reversed. So, by conventional current flow, the current will flow from the positive terminal, then going to the negative terminal. So the current will flow from here, going to the resistor, and then going to the diode. Note that this end of the diode is the positive terminal, and this end of the diode is the negative terminal. Since this is the correct polarity, then current will flow continuously. Then it will go back to the negative terminal. Thus, we have a complete circuit. This condition is called forward bias. On the other hand, since the battery is reversed, current will flow from here, going to the bottom, then going here. Again, this is the negative side of the diode, the positive side of the diode. We all know that a diode allows flow of current in one direction only. Since current cannot flow from negative to positive, thus the diode will not allow this current to flow. Therefore, we don't have a complete circuit. Current will not flow. This condition is called reverse bias. The next component is the switch. The switch allows flow of current by opening or closing itself. In its very basic form, a switch here has two terminals. If the switch orientation is like this, then this is open. Current will not flow, since there is no connection between the two terminals. If the switch position is like this, current will flow because the two terminals are already connected. Switches come in multiple numbers of terminals and multiple number of circuits. I have here a circuit involving a switch. We have a battery, a switch, a resistor, and a light-emitting diode or LED. It's important to note that the LED is an example of a diode that emits light when current flows. Now, the current will flow from positive going to negative for conventional current flow. Since the switch is open, there's no way that current can go from here directly to the resistor. So what we do is we close the switch like this, and then we have a complete circuit now. This one closes, so the current will flow to the resistor, to the LED. The LED will light, then go back to the negative of the battery. Now we have a complete circuit. Next up, capacitor and inductor. These components store energy in their body. The capacitor has two metal plates with a dielectric insulator in between. This setup causes electric field energy to be stored in the dielectric. The capacitor symbol is like this. That's why we say a capacitor has been charged or discharged. We're talking about the charge inside the dielectric. On the other hand, an inductor is made up of a coil or just a wire that has been winded up or coiled up. The inductor stores magnetic field energy in its core. The core can be a ferrite material or any magnetic material or even air or coreless. Other variations or devices based on the inductor are transformers and other devices that have coils. In this example, we have a primary winding and then a secondary winding with the core in between. Next, transistors. We will discuss two types of transistors, the bipolar junction transistor or BJT and the Mosfet transistor. The BJT is a three-terminal component. Its terminals are the base, the emitter, and the collector. It's usually used as a small signal amplifier, meaning a small input current at the base will cause a large output current between collector and emitter. A MOSFET transistor is also a three-terminal component. Its terminals are the gate, the source, and the drain. Like the BJT, it can also act as an amplifier, wherein a small voltage input at the gate will cause a large current output at the drain to source. But more commonly, MOSFET transistors are used as electronic switch, meaning the input is the control and the output is the switch. For example, I have here a 3.3 volts input. What it does to the output or the drain side is that it switches the voltage from 3.3 to 0. Then if the input is at 0 volts, it makes the output switch at 3.3 volts and vice versa. MOSFETs, when interconnected with each other, become the building blocks of logic circuits and microprocessors. Finally, we have the integrated circuit, or much commonly known as IC or just chip. An IC, or an integrated circuit, is a collection of electronic components integrated into a microchip. This microchip can have different functions, for example, as a microcontroller, or a microprocessor, or a logic circuit. This microchip can have different electronic components that we have discussed so far. Inside it, it can have resistors, capacitors, MOSFETs, BJTs, switches, and many more. What are analog signals and what are digital signals? Our physical world is actually analog in nature. Our body has many sensors that detect those analog signals from the physical world. Example, our eyes are our sensor for light. Our nose are our sensor for smell. Our tongue, our sensor for taste. Our ears, sensor for sound. And our skin, our sensor for touch. Analog signals are voltages that vary smoothly and continuously over time. The keyword here is continuous, meaning it has specific value at every point in time. So it can either be DC or AC. Analog signals can come from different sources like analog microphones, analog video cameras, and analog sensors like light sensor, temperature sensor, gas detection sensor, motion sensor, and many other sensors that detect other physical parameters. We'll discuss more sensor types in a bit. Digital signals are discrete signals, unlike analog signals that are continuous. They have a finite set of values only, unlike the analog that may have infinite set of values in the time base. Digital signals are binary in nature in that their value is expressed in two states only. Usually we express them as 1 or 0, true or false, on or off. Most signals in modern electronic systems already use digital signals. Here's a simplistic illustration of analog signal versus digital signal. For the analog signal, you can see that it is continuous. For the digital signal, it is discrete, represented here as a binary number 0 and 1. Here's another illustration of analog versus digital signal. I have here two sets of signals. The red one is the analog and the blue one is the digital. Notice that the analog signal is continuous. It has values at all points in time. Unlike the digital, they only take 4 values across all the possible values of the analog signal. We have this point as one value, this point as another value, this point another value, and this one. We have 4 values. And each value of the digital signal is expressed as a 2-digit binary number. In short, we've divided the whole range of analog signal into 4 points only. For example, this one. This point has a specific analog value. The digital value is 1, 0. At this point, the analog has another specific value, but the digital has no value at this point, so it can only take either this one or this one. Next, at this point, the analog has a peak value, but the digital will take the 1, 1 value at any of these analog points. This is why we can say that digital signals are discrete signals and not continuous. Now, let's take the same analog signal but subdivide it into 8 digital discrete points. What we've done here is, since we subdivided the signal into more discrete levels, the resolution is finer. When I say resolution is finer, it means that the staircase levels here are much more smaller, giving us more accurate values for our digital signal equivalent. Since we have 8 points, we're using 3-digit binary, 0, 0, 0. This is equivalent to value of 0. 0, 0, 1, this is 1. 0, 1, 0, this is 2. 0, 1, 1, this is 3. 1, 0, 0, this is 4. 1, 0, 1, this is 5. 1, 1, 0, this is 6. 1, 1, 1, this is 7. Okay. So, again, for this specific set of values for analog, it will take 0, 0, 0 or 0 as its digital equivalent. For this point, it will take 0, 0, 1 or 1 as its digital equivalent, and so on and so forth. Let's say that our analog signal here has specific voltage value. Let's say this is 0 volts, 0 volts, and then the peak is, this is 5 volts, and then the negative peak is negative 5 volts. Okay. Let's say that I have a value here. Let's say this is around 2 volts. In analog terms, the red line, this is 2 volts. If converted to digital, this is 101 or 5. Let's say I take the value here, this point. In analog terms, this is, let's say this is around negative 4. Let's just assume, not to scale. And then the digital equivalent is 0, 0, 1 or 1. Okay? Now, just an additional point. If we increase the number of levels for our discrete signals, let's say we have 16 levels or 128 levels or 1000 levels, what do you think would happen? If we increase the number of digital levels, it just means that we have a finer resolution, meaning we have a very small staircase size here, such that the digital signal already approaches the analog equivalent. That's why when we say HD or high definition, it means that you have more digital pixels in it, such that when you zoom into the picture or movie, you see that the pixel is very small compared to when you have a small resolution or non-HD. When you zoom into the picture, you see the very big pixels because of the same principle. It is also important to note that the number of bits used in the digital system will determine the resolution of the signal. Let's say we have 2 bits only, like our first example. 2 bits will translate to 4 digital discrete levels. And then 3 bits will translate into 8 digital levels. So the formula is 2 raised to n, where n is the number of bits. Therefore, if we have 10 bits of digital signal, then we have 2 raised to 10 is equivalent to 1024 digital discrete levels. So that's why in computer systems, you commonly see the pattern 2, 4, 8, 16. It's the same with for example, if you buy a memory card, you see a 2 gig, 4 gig, 8 gig, 16 gig, 32 gig, 64 gig, and so on. Since our physical world is analog, but our electronics are digital, we need to convert analog to digital and then from digital back to analog. We need analog to digital converters, ADC, and digital to analog converters, or DAC. Imagine a person here speaking. His voice is analog. The microphone is the sound sensor. It is an analog sensor. It takes analog signals from the person's voice. It goes through the ADC, analog to digital converter, and then the output of the ADC is already digital. And then we have a digital system which do some processing of the signal. Let's say the processing is, it increases the pitch or the frequency of the human voice. And then its output is, it will go to the DAC, or digital to analog converter. The DAC converts it back to analog so that when it feeds it to the speaker, which is an analog device, then we can hear the analog sound of the human voice again. Specifically for the Arduino, it has 10-bit ADC internally built in, meaning it can convert an analog signal from 0 to 5 volts into a digital value between 0 to 1023. Why is that? Since the first value is 0 and the last value is 1023, that's 1024 discrete levels. Let's sidestep a bit and discuss about the digital number system. The most common number system we use in our daily lives is the decimal. It is base 10, meaning we use numbers between 0 to 9. Computer systems or electronic systems use a binary number system. It is base 2, meaning it will only use 2 digits, 0 and 1. Since expressing a number or a character in zeros and ones only, it means that you will have very long strings of zeros and one for only one character. So that's why we have the octal and the hexadecimal number system. Octal, it is base 8, so you will only have digits from 0 to 7. Hexadecimal is base 16, meaning you will only use numbers from 0 to 9 and letters from A to F. Let's take some example of the digital number system. We have here values for decimal, 4-bit binary, and hexadecimal. If you have a 0 decimal, the equivalent binary is 0000, and hexadecimal is also 0. If you have a 5 for decimal, we have 0101 for binary and 5 for hexadecimal. If you have a 10 decimal, we have 1010 for binary and A for hexadecimal. Notice that values more than 9 takes a letter. And then for value of 15 decimal, we have 1111, and equivalent hexadecimal is F. In digital systems, it is common to use binary logic states to describe a condition or a comparison. In Boolean logic, it will only take 2 values, either true or false. In Boolean algebra, true is equivalent to 1, and then false is equivalent to 0. If we will use a positive voltage state, 1 is equivalent to high and 0 is equivalent to low. In terms of Arduino, high is equivalent to 5 volts and low is equivalent to 0 volts. On the other hand, we can also use a negative true state, meaning we just reverse the logic. 1 will have a low or 0 volts and 0 will have a high or 5 volts. But most commonly, we just stick with the positive true voltage state, which is 1 is equal to high or 5 volts and 0 is equal to low is equal to 0 volts. Let's discuss sensors and actuators. We define a sensor as a transducer that converts a physical stimulus from one form into a more useful form, which is usually electrical, to measure the stimulus. If you have a light sensor, it is actually something like an optical or mechanical type of sensor. There's a transducer that converts it to electrical signal, and then that electrical signal feeds to our Arduino or microcontroller. There are two basic categories, analog and digital sensors. For analog, we've already discussed this. It gives you a continuous value. For digital, it can either give you a binary output via digital communication protocols, or it can give you a pulse output, like a pulse counter. Now, let's see some examples of sensors that we can interface with the Arduino. This is not an exhaustive list, but just to give you an idea of the different sensors that we can use or integrate. We have machine vision or optical or ambient light sensor. So you can use a camera to take photos, or light sensor to measure the ambient light from the sun or the environment. Acceleration or tilt sensors. If, for example, you're building a drone, so you need accelerometer to measure the movement, maybe a gyroscope to measure the tilt. If your application is measuring the power consumption of a building or a house, then you will need an electrical sensor like power sensor, current sensor, or voltage sensor. If you're detecting leaks in pipes, there are leak sensor, or the level of a river or stream, there's a level sensor. If you are measuring weight, there's a load cell or torque sensor or pressure sensor. Flow of liquids or water, there's flow sensor. Gas sensors or chemical sensors, there are many gas sensors, like if you want to measure carbon dioxide in the air, ammonia or methane in the air for example, for a poultry, and dust, maybe dust particulate in the air. So you can use all sorts of gas sensors. Sound, acoustic sensor, humidity and temperature sensor. Of course, temperature is the amount of heat, and then humidity, amount of moisture in the air. Position, presence, and proximity sensor. Can use a GPS module for this, or an infrared-based proximity sensing. Okay. So you can interface almost any sensor to the Arduino. Just take note of the physical interface to the microcontroller or to the Arduino. If it's analog, the voltage range should be between 0 to 5 volts, because Arduino only accepts 0 to 5 volts. If it's higher than that, then you need to convert first to that level. If it's digital, then you need to know what communication protocols Arduino supports, like I2C or SPI or the serial or UART, which we will have a small discussion later. Now, for the actuator, it is a hardware device that converts a controller command into a change in physical parameter, usually mechanical parameter like position or velocity. So, converting from electrical into a mechanical action. We have three common types: electrical actuators, hydraulic actuators, and pneumatic actuators. Electrical actuators, we have electric motors, which can be either DC motors or AC motors. DC motors, meaning you power them with DC. You have the normal DC motor, which if you put power on it, then the rotor of the motor will turn. There's also geared DC motors, meaning you place additional gears so that you increase the torque but reduce the speed. There are also servo motors, which you can control more accurately. Like if you want to control 0 to 90 degrees rotation or 0 to 180 degrees rotation, like that. For AC motors, you power them with AC voltage. These are more commonly used in industrial applications. So the way to control this is usually using VFD or variable frequency. Next, we have the stepper motors, where we can control rotation of the motor in steps. Like you can define the angular rotation that the motor will move. Another type of electrical actuators are solenoids. These devices have coils inside them wherein it acts as an electromechanical device. By energizing the coil, it activates a switch. For example, you have a valve. If you turn on the valve using a voltage signal, then the coil inside will activate the valve to open or close. Wherein, if the valve is open, then water can flow. If it's closed, water cannot flow. For pumps, it's the same concept. For locks, or for example, you're building a automated security or lock system, it's the same concept. You energize a coil, then it will control a switch or a lock, something like that. The other forms of actuators are the hydraulic one, which use fluid to amplify the controller command. So it uses fluid. This is more commonly used in industrial applications wherein you need to lift very large amount of weight or force. For example, hydraulic lift in car care centers wherein they can lift the car very easily. Pneumatic actuators, on the other hand, use compressed air as the driving force. So hydraulic, they use fluid. Pneumatic, they use air. This is also, again, more commonly used in industrial applications. Just notice the sound when the bus door closes. That's pneumatic, an example of a pneumatic actuator. Can we interface pneumatic and hydraulic actuators to Arduino? Yes, we can, but we need drivers or converters since hydraulic and pneumatic are mostly mechanical devices and Arduino is an electrical device. That's it for this lesson. In the next lesson, we will be learning about basic programming concepts as well as Arduino functions.